about like how you would design your, how would you design your visualization system, right? When when you have like, how do you approach a problem? Like how would you build a visualization system from scratch? What approach you're gonna take when you talk to like customers or scientists or users of some sort. How would you do that, right? So for example, let's pick a very simple example, like what causes the low mile per gallon for a car. Okay, that's like a simple example, right? So you start off with a data set, so like you have these salient features of a car: miles per gallon, top speed, acceleration, number of cylinders, horsepower, weight, and country origin. Let's say you have 400 cars. Okay, now you can basically study the system of car and figure out like these questions that you have, right? So you have this spreadsheet here, but that doesn't really tell you much. Then you can do you can build a correlation graph that we talked about, and actually you can build a causal model out of that. Let's not talk about how you build a causal model, but there's algorithms for that can take correlation model and turn it into a causal model. But it basically tries to explain a few things for you, right? Like based on causal analysis. Here's like this causal graph. For example, you learn that the weight of a car causes the mile per gallon, right? So if you have high weight, you have low mile per gallon, right? That's like the red R arrow here. It's like a causal one. Then when you have the model here, doesn't really have a lot of effect here. But another thing is if you have number of cylinders, the more cylinders you have, the bigger the displacement will be. Like when you know something about engines, displacement basically means the amount of, basically means how big the engine is, like the size of the pistons and so on, right? So that's basically tells you this. So if you have more cylinders, you have more pistons, and therefore you have more displacement. And then when you have more displacement, you'll get more horsepower. Like the bigger the engine, the more horsepower you get. And then the more horsepower you have, the less time it will take you to go to 60 miles an hour, right? So that also makes sense, right? And the more displacement you have, the bigger the car is, the bigger the weight will be, right? And the weight will also, but the weight has this problem again that that the mile per gallon go down, right? So this is basically sort of a conflict now, right? You want the big car, at the same time you want the low weight, right? You want the fast car, the same, so it's kind of a conflict. So let's talk about this sort of problem here and turn about the how would you design a system that when someone wants to basically ask this question, what is the cause of low mile per gallon? Like analyze this, how would you go about it, right? So this is this just isolating low mile per gallon. Like here, weight causes this and weight this, right? So this is based on network only with regards to mile per gallon. So this is a chain. This is the causal chain, right? The more cylinders you have, the bigger displacement, the bigger the weight, the lower the mile per gallon. So it's like basically just unrolled. So let's talk about how would you build a visual analytics solution based on this. So let's use what there's a very interesting paper that I encourage you to read called the Nested Blocks and Guidelines Model. That's like sort of talks about how do you create a visualization system. This is a good paper to read. There's a few more books that these two people have written, Sedelmeier and Munzner, 4 papers, but this is a good one. So basically what you want to do is you want to analyze the problem, right? So you say you meet with some users, initial contact with some business users or whatever, right? And then, or scientists that know nothing about visualization or very little about it, other than a bar chart maybe, and they basically, all they have is like a task, right? They have some task. And usually this task is described in domain terms, so they have like, I want to know why my car takes, I want to understand this, right? Or something like this. So basically eliciting the requirements is notoriously hard, right? Because when they come to you, they don't really tell you what they really struggle with, right? They just tell you they have this problem, but they can't really they cannot verbalize what they struggle with. So what you usually have to do, really what you should be doing is just go and observe them and see how they perform their task. How do they actually work in their office or whatever? Like how do they usually find the solutions for their problems? Okay, what the kind of do they have? And then you observe what the pains they have, right? What kind of trouble they have, right? Observe them, right? You just let them work and then observe them. Don't ask, let them actually explain what they do. And then you discover what the limitations are, right? What are the limitations of this? And what's currently impossible, slow, or tedious. They will tell you that, right? Oh man, it's so hard to do this, it's so hard to do this. And then you see, oh, it's so slow, it's really the struggle, right? So you observe that, right? This is basically where you observe the problem, right? You characterize it, okay? And then what you do, after this so this is basically what we call domain problem characterization. You just, in very layman term, you write down what they struggle with, okay? And then, no solution there. You don't have any solution at this point, you just observe, okay? Then the next thing is you try to find out, you abstract this into a design, okay? Just come up with no visualization, no nothing, just the design, like map from the domain vocabulary to the abstraction, okay? So you need to do some sort of transformation. So the data types are still described in abstract terms. There's the numeric, there may be tables and the networks and spatial organisms like plots and things, but no visualization at this point, right? Everything is abstract, okay? They may have some generic activities from the interaction. Remember the interaction lecture I gave? Sort, they may have sorting tasks, or they have filter tasks, they have correlation tasks, trends, they find trends and outliers. Those are sort of kind of things they do, right? Because that's what you usually do when you try to solve a problem, right? You try to filter out stuff you don't want, try to sort things a little bit, and this is basically what you're trying to do, okay? Figure out what these basic things are that they do. And then this basically becomes the data operation abstraction design, okay? This is the next box. Remember I told you it was the nested model, right? Nested model. So we're gonna nest the model, right? First we characterize the problem, then we'll abstract the data and operations, what they actually do, right? Stuff they do. And then you find a visual encoding, right? How you best show the data that they have, okay? Is it like, do you want to use a bar, pi, line chart, or polar coordinates, MDS, but scatter plot, tree map network, right? Something, how do you show it? Okay, how do you show this best, And then how do you best support the intent the user may have, okay? Select, navigate, order, brush. Okay, these are like selective intent, right? And that basically now is an encoding. Okay, now you come up with an encoding. Okay, and then at the very last moment, you actually make an algorithm. Okay, after you've done the encoding, what works best for them, and you keep talking to them, right? You keep talking to them. Then you come up with the algorithm that actually does this. Okay, that will support human interaction. And that basic visual analytics part of it. And that's the algorithm design. That's the very end, right? First characterize the problem, abstract the design, encode interaction, and then this, right? So let's talk about this causality analysis framework I just presented. Okay, use the car design example. Okay, so first, domain problem characterization, how to design a faster car without elevating gas consumption. That is a problem they have, right? When you have a car manufacturer, how to design a faster car without elevating gas consumption. Okay, so how do you do this, right? So domain abstraction design is basically this is the very simple problem they have, right? Now, the abstraction is determine how the different car parameters depend on one another, okay? And then collect data of different car models in computer causal network, okay? So this is the abstraction, right? Because that's what they want to know, right? They want to know how to design a faster car without elevating gas consumption. So this is the abstraction. Now you figure out what are the players here, car parameters, and how they depend on one another. Because you explain it, right? You want to explain it, and then collect the data of different car models and compute this causal network. Because this is where you start to try to build a model that can help them design the car, that figures out what is underneath, right? And then encode it into a technique. So you draw a graph, the parameters are the nodes and the causal links are the edges, right? Because that's how you usually show a causal network, right? You make nodes and causal links, okay? And then you provide the interactions that allow users to test causal links in computer's core. And at the very last end, you compute the algorithm, okay? The algorithm that you want to do. And this is really, this is really how you go about, right? And then in the end, you have this kind of network, right? This kind of thing here. You compute a causal model, then you explain it like this, and then with nodes, that's basically, and then people can start working with it, right? They can start, figuring out how things are. Okay, so that's really how the iPhone came about. I mean, if you don't know the story how the iPhone came about, that's really how it came about, right? Steve Jobs, he characterized the problem, then abstracted it, encoded it, and did the algorithm, right? So, then you got the iPhone, right? Because Steve Jobs, I don't know if you saw the movie or if you know the story about how the iPhone came about. It started out with this iPod, right? Steve Jobs was, he was frustrated by a CD on the Walkman, right? Because it was so clunky, right? And it didn't work, and there was only a few songs on it. I had to change it all the time. He was really frustrated by it, and so he thought, I can build a system. I'd love to have a system that you can play as many songs as I want, right? And you can easily find them, right? Don't have to swap out these CDs all the time. That was the first thing, and then he, thought about it, and then he designed the system around it, right? Same thing with the iPhone. He wanted to have this phone that at the same time comes and send also email and surf the internet, right? How do you do that, right? So that's what he wanted. He didn't know exactly how to do it, and then he slowly designed it, right? Like this, bought a phone company, like a phone company, I think, from Germany, that made the hardware for the phone, right? And designed the phone, and then came up with ways how people can quickly access apps. Like he actually invented the word app, right? I mean, he came up with this too. So the same thing, right? He basically did the same thing, right? He first had built this domain problem, and then he abstracted it, and then he encoded visual technique, and then he made it happen, right? That's exactly how to do it, right? So you really want to, when you have a problem in anything that you want to solve in terms of visual analytics or something else, always use this kind of nested model, right? So here are the threat, right? So this is for the first time, right? When you have the problem, right? You may have the wrong problem. You observe them and interview them and make sure that you actually analyze the right problem, right? Don't make sure, and then validate that by observing the adoption rates once you have the system, right? Don't try to address the wrong problem, right? Really make sure that you got the right problem, and then observe the adoption rate. And then the threat could be here in the abstraction stage, that you don't have good data, right? That you can't abstract the operation that good, right? So validate. You can test it on target users. Do a little bit of a user study beforehand, right? Do a field study, and really do what's called a Wizard of Oz model, right? Like figure out how they would do, right? And then the next one is when you have a visual encoding. Maybe the encoding that you chose is not good, right? The interaction technique is not good that you chose. Then you got to justify that, right? Actually, again, work with users and make sure that this encoding actually works for them, right? Validate with users, on any users, right? Really make it like not just the target users only. You really try to use it with a lot more users than that, right? And then finally, you do the algorithm. The threat is that the algorithm may do too slow, doesn't support the activity, so you got to make sure that you validate by analyzing computational complexity, and then measure that, right? Make sure it actually computes as fast as you want it on the platform that you intend. And then you implement the system, okay? So only here you implement the system. Everything else is just, playing around and try to come up with mock-ups, right? Always use mock-ups first. Don't implement a lot, right? First mock-ups, talk to people, make sure they like it, called the Wizard of Oz design. You simulate a lot of the operations. You actually don't implement them, you just simulate them. Like you may flip through slides, for example, instead of like when a user clicks a button, you don't actually have that going on. You just flip a slide. What would happen, right? If you had clicked that button, right? You just have another slide with a screen on it. So that way you don't have to implement it yourself, right? So at the very last you want to implement, because this costs a lot of time, right? Now there's this Python, of course. There's a lot of things you can do, prototyping that you can do, which is very cheap. So you can actually afford to implement a few things because there's lots of libraries on it, right? They may not be fast enough, but they will do what you want to do. So there's a lot of things you can do with, like, but you're never going to implement the full system, all right at the beginning. You do slow steps, right, until you get to that point, right? First, figure out that you build the right problem, figure out that you have the right abstraction, that you know how you really abstract it into operations. Make sure that the visualizations work, that the users don't hate them. Then make sure that the algorithm is actually going to be fast enough, just by analyzing the complexity, and then actually implement it, right? So this basically, this is basically how you really should do system design, right? In visual analytics, but also other things, right? Visual analytics has one thing that you have to have visual encodings, right? So visual analytics this particular pipeline is really gauged for visual analytics, but this nested model really applies in other places too. Then you need to do a user study, right? Formative user study is the one that I just told you about, right? You really have the user in the loop all the time. You have the user in the loop all the time, right? You never always work with target users, and then slowly, first you have just some of the users, and then you fan out and find more users, right? This is also called a focus group. Work with these people and then conduct this formative user study. It's formative because you form the product as you work with users, right? There's also another one called summative user studies. That's the other one. That's the way around. That's the other way around. You basically make the system and then you test it. Usually what happens is you make a formative user study developing the system. And once you have it, you do a summative user study with more users to evaluate it actually that it really works, just to make sure, right? You can do in the wild on Amazon, or you can just go and find a lot of users around, or you do it in the laboratory. You usually do a smaller number of subjects, but let them speak. Okay, so this is called the speaking aloud protocol, where users will use the system and then they talk what they do. There's also something called heuristic analysis, where you basically have users indicate what they didn't like and let them judge it, how bad it was, right? Is it just a small thing, or is it much bigger, or is it very severe? And then you improve the system as you go, right? And keep asking them a few times. There's a theory that oftentimes you only need 3 to 5 users to figure out all the flaws in your system. There's a paper by Nielsen that showed that you actually don't need a lot of users, right? 3 to 5 users may be enough. 7 users may be enough to really, because every user will find a few flaws, right? There may be some of flaws may be so severe that the users all find them. But some users find this flaw and another user finds another flaw, has a little different objective, right? But you don't really need that many subjects, right? There's also the other way around. Of course, if you want to do statistical testing, right, then you need to do a power analysis. Figure out like how many users do you need for a particular effect size, right? Let's say you have a certain effect size that you want to test, like twice as good than the competing design, or 4 times as good as the competing design by some measure like time or accuracy. Then you can compute by a process called power analysis. You can compute how many users you will need to actually verify this. So you'll do a little bit of a pilot study first, figure out how big your expected effect size is, and then you can compute what's called a p-value. And I'm going to talk a little bit more about this in the next slides, You know, it can compute something called a p-value, and then that you can figure out how many users we'll need to actually verify this effect size, you know, statistically significantly, right? You cannot just come up and say, you know, 10 users liked it, better than my design better than the other. It has to be statistically evaluated. I'm going to have some slides on this next. You know, you can do this crowdsource of internet. You know, what's nice about if you crowdsource the internet, you can get a lot more subjects, but then you can't do the speak aloud anymore, right? Because once they're like internet users and they're like, you know, hired by Amazon Mechanical Turk, then it's hard to get some opinions from them, right? They basically just solve the task and then they leave a trace based on that, but you cannot really, they don't give you much feedback. But when you actually, you know, meet them in your laboratory or meet them somewhere, you know, then you can actually analyze what they say. And what you can do, you can transcribe what they say. You can group things they say. Some people say something about performance, so then you can group it all in the performance utterings. Some people say something about the interface. Then basically you let them talk, and then you just take all that stuff, what they say, and group it into different bins. You know, the performance bin, interaction bin, the aesthetic bin, and the usability bin, whatever it is, right? You make a bunch of bins, and then you evaluate how they have said it, right? Have they liked it? Have they found flaws? Have they, did they think it was superior or inferior? Did they compare it with other products? Did they struggle, right? So these are all the things you can get, right? So really, when you make a system, you know, now you have your the final project system, right? I mean, maybe you can test it with a friend or two friends or maybe more, you know, and present a little bit some impressions that your friends had with the system that you're designing for your final project. It's not mandatory, but it's a nice touch, right? If you can show that, you know, stuff like this. So anyway, is there any questions about this? So how do you design a system? You know, so this nested model, very important, right? Whatever, I really like this. First the problem, then abstract the problem into something that you can get a hand on. Then you find the visual representations for this and the interactions, and then finally design the algorithm that actually does this, right? You know, so this, and then this whole thing with this part here, right? You know, how do you actually do this, right? Formative user studies versus summative user studies. How many users do you need? You know, and you know, do a power analysis, figure out, you know, for a given effect size, how many users do you want, you know, to make it statistically significant, and then you know, and then you let them speak aloud to actually, so you learn what they think about it, you know, and what they struggled with. You know, just let them speak what they're doing, right? They may be searching around, oh, I can't find this button, where is it, you know, or they say, oh, this is great, you know, I really found this immediately. Encourage them to speak while they do things, right? And then you may be recording it and analyzing it later. Okay, so that's kind of like what I wanted to say about this very general stuff of like system development, and make sure that things go the right way and actually successful in the end. Okay, if there's any questions, then put them in the chat window. Otherwise, I'll go and talk about the user studies themselves. Okay, so this is the user study, user evaluation. So, you know, so user evaluation, right? So, you know, so here's like a scenario, right? So now, you know, your boss asks you to come up with a visualization that can show 4 variables, right? So let's say you're not as high up in the totem pole yet, right? You have a boss, you know, you ask you very specific things. Your boss didn't ask you, go to these clients and figure out what they want, right? Your boss is like, you know, asks you actually very specific things, right? Ask you to come up with a visualization that can show 4 variables, okay? Then that reminds you what you had in 564, right? And you remember these visualizations, right? Your scatter plot matrix, para coordinates, tree map. And then you're gonna ask yourself, you know, which one will you implement, okay? So, you know, so then you'll ask, let's ask your best friend, okay, like which one you wanna do, right? But, you know, it will not be an unbiased judge, right? Of course, your friend will say, "Oh, take the one that you've been always working on, right, for the whole time, right?" And, then it's not going to be unbiased. So you can ask more people. That's probably a better thing, right? Because more people, they will, especially when you don't know them, they will tell you a lot more of the truth than your friend, right? And then what you will need is you need the implementation, okay, and some users. So, you need the implementations first because you want to test them on some users, right? This is where you move beyond, right? This is like the summative part now, right? The summative user studies. You already have an implementation now. And then you need a few tasks because they need to do something, right? So you need to evaluate them doing these tasks, okay? Then, ask user maybe, find certain relationships in data or find certain data elements and so on, right? Like typical tasks that that you have to do when you do a visualization, right? You have to find relationships and find data elements or find maximum minima, all these basic tasks that we talked about, right? And measure the time and accuracy that they had solving the task using the visualization that you have given them, right? And do this for each of the 3 visualizations. So let's say you get a result like this, right? Let's say you have 12 participants. And each of them had certain values, okay, for task 1 and task 2, device 1, device 2, device 3, like this could be visualization 1, 2, and 3, or visualization implementation 1, 2, and 3. And they solve 2 tasks, and each of them, this could be time or accuracy, measures this, like they basically perform doing this, okay? And then you can compute the mean for each and the standard deviation, okay? And then, you can look at it, right? You can say mean, oh, this is almost the same. This one is, this is better, seems to be better. This task 2 seems to be better than task, So let's look at it for here, right? To make a bar chart, okay? So task 1 is the green, task 2 is the orange, teal, right? And then you'll see, okay, task device 1 and 2 and 3. Okay, device 3 did a lot better for task, if this is the task completion time, the task device 3 did a lot better for task 2. Didn't do so well for task 1. Actually, they all do the same for task 1. This one, device 1, really doesn't do well for task 1 at all, right? It took a long time to do, okay? So which visualization is best, 1, 2, or 3? You might think 3 is best, does about the same for task 1 than all the others, but it really excels for task 2. Okay, so you would say that. But is this really true, right? So you ask now also, could be gender bias, right? Assume your boss is female, right? But the cohort is male and female users. So, so it depends now. Do females prefer one visualization over another, right? That depends, right? You may, if you want to impress your boss and make the boss appeal, let's say, your boss wants to get this visualization and he's just going to judge it. Maybe you want to use the visualization that goes better with the females than with the males, right? And then you're asking yourself, of course, because you're not going to just make visualizations only for females. Do females actually prefer one visualization for another, right? Could also be young and old people, or U.S. citizens and non-U.S. citizens, or whatever it is, right? Like it could also be more than 2 classes, right? Whatever it is, could different whatever it is, right? Age groups. Anyway, you want to use the one, right? So is there a gender bias? So let's look a little bit about basics, okay? Like basic statistics, right? That you may or may not know, but you hopefully remember. I hope so. But just to be on the, just to refresh your memories. Okay, so you have this normal distribution here. Most of these things assume that data are normal distributed. Okay, which is not always the case, but let's, most of these analyses assume it, so then basically what it looks like, here's the mean vector mu, and then 1 standard deviation, 2 standard deviation, and then basically 68.2% is captured in one standard deviation, and 26 more within the two standard deviations. After the 3 standard deviations, really everything is inside, right? So, so that's basically what the normal distribution does, right? And then you have this concept of regression, you want to explain the variation in a dependent variable using the independent variable, right? So you want to build this regression model, right? And it's like, it's an explanation of causation, of course, not necessarily. It could be spurious, but anyway. So these parameters that go with regression is basically this intercept here, B0. This is how the offset from the curve from the 0. And the B1 is the slope, right? Delta y over delta x. And then you build this regression model, this regression line here, B0 plus B1 times x plus epsilon. Basically, epsilon is the random residuals, right, from that, right? So you basically have a prediction here, which is you have the observation y, and the prediction is given by this regression model, this y hat, and then this difference here is basically epsilon, right? So observation is here, prediction is here, and this is the 0 line, okay? And then basically this is a simple linear regression, okay? This is called the prediction error. This is the prediction away from 0, okay? And 0 is this, okay? So what we call it actually is this y. This is explained by it. This is epsilon. This is the part that's not explained, okay? So this basically looks this E-squares regression, that what you usually use to do regression modeling, picks the line where the sum of squared error is the smallest, right? That's what it maximizes for, right? It tries to, find that line that minimizes this sum of error, okay, squared, okay? And this value is basically called the sum of squares of error, SSE, right? So population mean is the mean of all the observations. The sum of squares regression, SSR, is the sum of the squared difference between the prediction for each observation and the population mean. So this is the sum of, this is the regression, okay? This is the prediction minus the mean squared and summed over. That's that, right? So we get these things, right? The sum of squares, we get this SSR, which is the prediction minus the mean, and SSE is the error, this is the observed minus the predicted, and both of these become what's called the total sum of errors, sum of squares. Okay, this is basically both of it. Okay, so now let's look here, hypothesis testing. Okay, we want to do hypothesis testing. Hypothesis testing basically, and you need this, right, because you make a hypothesis that your product is better than the competing one, right? That's what the hypothesis is, and you're going to test it statistically. So so you may come up with a statistical procedure, right? It's the time to complete a task less using method A than using method B, right? For example, method A would be your implementation, method B would be the competing one, right? And then there's basically statements you're going to say, there's no difference in the mean time to complete the task using my method and the other one, okay? This is called a null hypothesis, assumption of no existence. You want to, of course, if you want your product to win, you want to reject it, right? You want to reject that null hypothesis. You want to prove that there is a difference between my product and the old one, right? So that's basically what you want to do. So what you're going to do is use basically is this what's called the analysis of variance, ANOVA, which is basically the statistical test for hypothesis testing and factorial experiments, okay? So basically the goal is to figure out if an independent variable, which is the time, has a significant effect on the dependent variable, which is the, So the time is the dependent variable and the independent variable is your product, right? So remember, the independent variable has at least two levels, test conditions. So like your product and the competing one, or your product with two different variations, right? So the independent variable is your product, and the dependent variable is the time or accuracy. And you want to see if there's a significant effect between your model and the competing one on the dependent variable, okay? So basically that's what you want to see, okay? Determine if the test conditions yield different outcomes on the dependent variable, one of the two test conditions. Okay, so what's really why if we the question often people ask, like, why do we analyze the variance when we're really looking at the means, right? Because we look at the means, right? We're saying, is the time complete a task less using method A and B, right? Which is the mean, right? But you know, we're actually looking at the variance, right? So why is that? Okay. So let me give you some examples here. Okay, so here's an example. Example 1, number 2. So here, same mean, 4.5 and 5.5 for method B. Again, 4.5 method 5.B. But here, the difference is significant and difference is not significant. So that's interesting, right? It looks the same, right? If you naively plotted this just by the mean, then you would, you know, this would look like, you know, of course it's different, it's 5.5 over 4.5 is 1 better, you know, whatever, 1 second, there must be better, right? But you're forgetting in this that you're testing this with users, right? And those users are not always the same, right? They're not robots, right? They have fluctuations, right? So significant implies that in all likelihood, the difference observed is due to the test conditions, method A and B. You know, not significant implies that the difference observed is likely due to a chance. Okay, there may be other things hidden to you, or users themselves had factors, right? And some maybe you tested method A with really experienced users, and method B you tested with really poor, you know, with really not experienced users, right? Of course, you biased it now, right, by experience, right? So yeah, that's of course terrible, right? You didn't, you know, that's of course terrible, right? You got to have the same class of user test both of these, not bias it. So now let's look at it, right? So basically, you have to look at these variations, okay? Then you'll find out. Method A, those users had a standard deviation of 0.68, and method B had 0.72, right? They look at these bars, right? You know, so you know, that's a pretty big, you know, so error bars, you know, is the root. That's basically you look at these with these caliper plots, right? So this is also within subject design, basically, because every subject does both methods. So number one thing you want to make sure is that these participants are randomized, right? You know, it actually doesn't really matter here because they're gonna look at both methods, right? They're gonna do method A and method B, but you got to make sure that you randomize this. Like some participants start with method A first and then method B, and some participants start first with method B and then with method A, right? So you know, you got to make sure, because there's learning effects, right? So maybe you do method A, you learn a lot about method B, right? You know, let's say there's a visualization. Once you use your visualization to system, then you'll already know a lot about the data, right? And then you do method B, and then you're much faster because you already know something about the data. So you got to use, of course, different data too. You know, don't let them, let them use the same data for both methods, right? Similar data, but not the same data. So there's randomization is very key in all of these things. The only thing, everything has to be random except the two methods, right? Method A and B. Everything has to be random, right? Orders have to be random. Data sets that they use have to be random. You know, you don't have any effect interacting in affecting this, right? Where you have systematic errors based on something, because maybe method A always used an easier data set than method B. You know, of course, that would be terrible, even though some people use method A and then method B, and though some people use method B and some first and then method A. If they have an easier data set for method A than B, of course, they will do better with A and B, right? So you got to make sure that they also, sometimes A use the difficult data set, presumably difficult, and sometimes method B uses the difficult data set, right? You got to randomize everything, really make sure, right? Otherwise, you're going to get favorable results or not, or other results may be against you, right? Who knows, right? So if you randomize everything, only keep, and only keep those things different, then you're going to be fine. So reject or not reject. So basically you measure these time, right? Then there's a slow overlap, right? What we've seen. Method B, there's some people that used less time for method B, and some people used lose more time for method A. So what you want to do is you want to take these distributions. Remember, we assume normal distributions, take them apart, right? Pull them apart. And basically, when they're sufficiently apart, we call method B different than method A. In this case, have a higher accuracy or lower or higher time, whatever it is, right? Once this is sufficiently apart, then you basically reject this null hypothesis and say method B is different method A. Okay, so now what you do is this. you build this table, okay? So we're gonna build the sum of squares, okay? So the mean square. So let me just explain what this means, right? So this is the probability of obtaining the observed value if the null hypothesis is true. So basically, this is the sum of squares. I have a little bit of a visualization here that shows this, okay? Just have to move this around. So go here, right? So basically, this is the sum of squares between the groups. And this is the method that is within the groups. This is like, if you have 3 visualizations, remember what we said, 3 of them, right? You want to see an effect, right? You want to see that this is better than this. So first there's this visual, that there's this variation within the visualization, within the method, and then there's the visualization across the interaction across the sum of squares between the methods, right? The difference between the methods. So this is basically, so you want to keep this small and this big. If you really want to show an effect of this being better than this, you got to make this variation small and this variation big among the methods big. And this is basically what this calls here. This is the subject sum of squares, this is the method sum of squares. The subject sum of squares is this within the variation, within the group, within each of these test conditions, and the method one is the one across it, right? And then you really want to see, the sum of squares is basically the sum of squares over the degree of freedom, right? The degree of freedom is basically how many subjects that you have. In this case, you had 10, I think, 10 subjects. Degree of freedom is based on the number of subjects minus 1, because they estimated a mean from that, right? So now this is within the subjects, okay? And the method, you have 2 methods, so degree of freedom is 1 because you computed the mean again, and then you go and divide the sum of squares by the degree of freedom, right? You want to like normalize that, right? The more methods you have, the bigger you make this, right? This mean square error is then smaller, right? Because the more subjects you have, the better you have accommodated for the variation, right? That's why you're allowed to divide by this, right? And then you come up with this, and then you divide this by this. This is the mean square within, right? You want to make this big, right? This has to be big because you want the variation. You want this variation. You want this variation to be small. The within, right? The within variation you want to make small, and the between you want to make big, right? This one you want to make big, and this one you want to make small. That's why dividing it. Then you get this F statistics, which is called 9.796 in this case. Okay, p-value should be below 0.05. That is basically the guarantee that these two distributions are sufficiently apart. This is measured by the t-value. This is the likelihood of them to be the same, right? The smaller the p-value is, the less likely it is that that one person here is accidentally in here, and vice versa. Right, so that's basically what this is. So basically what you want to have is like, you want this F statistics and this p-value here, right? You want this to be big, and you can get, how big you can get tables for that. And the p-value you want this to be less than 0.05. That's basically the likelihood. So usually 0.05. Whenever it is less than 0.05, then you're gonna be okay, right? If you use the threshold, right? Sometimes people use a 0.01 or smaller, 0.01 or even smaller, but 0.05 is usually okay. 5% likelihood that you make an error is okay, right? And then basically the way you report it, then you write it like this. The mean task completion time for method A was 4.5 seconds. This was 21% less than the mean of the 5.5 second observed for method B. And then it was statistically significant because the F value was 9.8 and the P value was less than 0.5. Okay, this is how you write it in a valid statistical way, right? And so now let's look at number 2, right? Number 2, much higher standard deviation, right? Look at this, right? I mean, it's almost, when you just look at this, they're almost overlapping, right? It's almost the same, right? Because this is so large, right? You can already see from here that probably there isn't really a significance between B and A, because within each of these methods is massive fluctuations, right? When you look at this, this is massive right here. This is massive, right? So this overwhelms the difference of the methods themselves, right? That slope is overwhelmed by this within the method variation, right? And then obviously, when you look at this, you get a p-value of 0.5, almost 0.5, which is way too large. So what this really means is that these distributions here are very close together, right? They're actually very close together. Method A overlaps a lot with method B. So therefore, they're almost the same, right? And the FL is very small, okay? And then you write it like this. The mean task completion was 4.5 seconds for A and 5.5 seconds for B. And then there was a substantial variation observations, and therefore it wasn't statistically significant, right? So that's what you would write, okay? So when you do your summative user studies and you measure parameters like accuracy and time, which are the most common ones, right? Like accuracy and time, right? That's what most people care about, right? Complete something faster and more accurate, right? I mean, this is that's everyone's dream, right? So you want to, those are usually the things that people estimate in most applications, right? Sometimes people like things better, but oftentimes people actually like, we found this, people may like things better, but actually they like things better that are less accurate. But they don't know that, right? They just like it, but they may not be more accurate, but they, so liking something doesn't really tell you that it's going to be better, right? Liking, of course, is good to get someone to buy it, but then someone to actually keep using it, right? Then that's a different story, right? So, liking, of course, is also hard. If you two methods that are both significant in terms of time and accuracy, but one is more liked, then of course it's great, right? Then you buy the one that's more liked, right? But you can test that too, but you definitely want to first test accuracy and time. Okay, so if you have more than two test conditions, you're going to have like this, then you get a lot more, right? Then you get these table here, and you get these standard deviations here, and you get the means for each of these test conditions, in this case 4. Then basically do the same thing, okay? You do the same thing, because that doesn't really pick. You'll just have 3 instead of 1 here, right? This degree of freedom, because now you had 4 methods instead of 1, right? Instead of 2, right? And now you have this 3. You can use the same table than before. You have a sum of squares of the within the test conditions, and then across here. Then you do again the same divisions, while you take this divided by 15 and this divided by 3 to get here. Then you divide this by this, then you get this kind of this F value, right? Then it's 4.954 and the p-value of 0.0047. Again, pretty good, right? The p-value is less than 0.05, which is good. So clearly there is something that's going on here. There is one method that is better than another, or maybe 2 methods that are better than another, or 3 methods that are better than another, but you don't know which one, right? So once you have done this, you know that there's something going on, right? Once you have found that there's a significance here for these among these techniques, then you know something's going on. But now you have to figure out which of these actually are different. And now you have to actually do a pairwise comparison. Okay, have to compare A and B, A and C, A and D, B and C, B and D, and C and D. Compare them and see if the p-values for each of them, for each pair, is like less than 0.05. And then, of course, A is better than C. Is it A? There's a difference between A and C, and there's a difference between B and C. I see. So C must be pretty good, right? So let's look here. So C has a higher one, right? So if this, whatever this was, like if this was accuracy, that is significantly better, right? All the others, they're sort of okay, right? They don't stand out. This one is not, this is why these are not different, right? A and B was not different here, right? A and B was the same, right? So really only C stands out, okay? And then, we showed that now by, you have to do pairwise. First, you do an overall one to figure out if there's anything going on. And then you do pairwise and figure out which one actually is different, right? Could also be that this is the only one that performed worse, right? If this were time, then all the other ones performed similarly, but this one was much worse, right? Then you're gonna reject, then you don't recommend C, but all the others, right? But maybe C was the only one that was significantly more accurate than A and B and C, A and B and D, right? And then you'll recommend C, right? Just depends what the dependent variable really was, right? In any case, statistics will always figure this out, right? Then there's another one, which is called the between subjects designs, right? Where you, before what we did was every participant tried both methods, but randomized in terms of the order in which they tried it. But sometimes you have a task that can only be completed by one particular person, right, and not the other, right? So for example, 2 left-handed users and right-handed users differ in the time to complete an interaction task, right? So you basically now you have left-handedness and right-handedness, but you'll either have a participant is either left-handed or right-handed, but it can't be both, right? You can't tell them now use it. You can't tell a left-handed user to now act as if he was right-handed, right? That would of course be terrible, right? So you have to this is what's called a between subject design, okay? Then you do this left-handedness, the right-handedness, you get means and deviations for both of these, left and right, and then you can do again the same testing, okay? And then the same thing appears. But in this case, it was not significant because the p-value was greater than 0.05. F-value was, there's a table for this, and then it also will say that it's not significant, right?